information security at Smarten spaces. His research interests include IoT, AI, cybersecurity, data privacy, and cloud and edge technologies. Vishwas has over 18 years of industry and applied R&D experience in those fields. Now, Vishwas is highly accomplished. He has been awarded the prestigious Maria Curie Fellowship twice by the European Commission and has contributed to several European R&D projects in the domains of IoT, the wireless sensor networks, and security. He is a senior member of IEEE and a member of IEEE IoT Community, IEEE Technical Society on Security and Privacy. He is also the present chair of IEEE Computer Society, Bangalore Chapter. Vishwas holds a PhD in ICT and wireless communications. So with this, let me hand over the podium to Vishwas. Now, just a few housekeeping. I'm sharing a few tips on how we could probably interact with the speaker. Currently, since this is audio broadcast, you cannot unmute yourself and pose questions directly. Rather, you can type your questions in the chat window. Both me, my colleague Chengappa, and Vishwas will be monitoring the chat window, and as and when questions are posed, depending upon the way the speaker would like to conduct, he may answer the question right away or may wait till the end of the session. So either ways, we will definitely make sure that your questions are answered. Okay. Now this session is being recorded. Now what we will do is that once the session is over, we will share the recording with Vishwas. Take his approval whether if he is comfortable with the way the recording has happened, and if he says okay, we will release the recording on a YouTube channel of IEEE Bangalore Section. Okay. So with this, let me hand over the stage to Vishwas. Over to Vishwas. Thank you.
Thank you, Prashant, and good afternoon, everyone. It's a pleasure to be part of the Skills Development Program conducted by IEEE Bangalore Section. And let me first share my screen. So just to confirm, Prashant, you're able to see my screen, right?
Yes, Vishwas.
Okay, great. So in the next 1.5 to 2 hours, we'll be going through these topics. In the first session, which will be about an hour or so, I will cover the overview of wireless sensor networks and IoT. I will take you through the IoT building blocks, end-to-end, how end-to-end security works in IoT, and why device management is required in IoT, and some of the tech directions. So once we are done with that, and with the overview behind us, we will go for the deep dive into some of the protocols that help build IoT. For example, the lightweight M2M device management protocol, the application protocol, the specific or specialized application protocol called COAP, DTLS security, and the 6LoWPAN adaptation layer on top of MAC. So we'll be deep diving into these 4 protocols, which are very specific to wireless sensor networks, basically the low power version of IoT or the wireless sensor networks. So I would suggest if you have questions, please keep them coming in the chat window. After probably every half an hour, I will take a look, and if it's very particular to the topic being discussed, we'll answer those questions. Otherwise, we'll have 15 minutes at the end of the session to answer any of the questions that you may have. Okay. So before we jump into IoT, I assume that many of the people or participants in the audience have some or the other background to IoT. Nevertheless, even if some of you are very new to IoT, I'd like to take you through some of the acronyms. IoT stands for Internet of Things. We also have the Web of Things, WOT. And much before IoT, we had machine-to-machine communications. Lightweight M2M stands for lightweight machine-to-machine communications. COAP stands for Constrained Application Protocol. DTLS is the datagram version of the TLS at the transport layer. And UDP is usually used in IoT and wireless sensor networks instead of TCP. UDP stands for User Datagram Protocol. So the datagram versions of both transport layer security and the user datagram protocol are present in IoT and WSN. And 6LoWPAN is a very specialized protocol for low power wireless sensor networks. And this is based on IP version 6. So it's an IPv6 based low power wireless personal area network. So all of us have heard about Wi-Fi, which is a local area network. And that is usually about 100 meters or up to a kilometer. And personal area networks are usually around us in less than 100 meters range, so 10 meters to 100 meters range. So some of the wireless standards that we usually come across. On the right-hand side, you can see wide area networks, metropolitan area networks, local area networks, and personal area networks. So wide area networks, we all know about many of them. And so are metropolitan area networks. For example, WiMAX was a metropolitan area network. Wi-Fi, which is a popular LAN network, 802.11. And personal area network, 802.15. The Bluetooth standard and the wireless sensor networks, which is 802.15.4, they all fall under personal area network. So some of those wireless standards are definitely used for IoT, and they depend on mainly the contact range. So if it is 0 to 10 meters proximity, we have very few technologies such as NFC and RFID. And some short range communications, 10 to 100 meters, we have many of those WPAN technologies, including Bluetooth Low Energy, Zigbee, Thread, Z-Wave, Wireless HART, and so on. And short to medium range, beyond 100 meters, we have the Wi-Fi networks. And in the range of 5 to 10 kilometers, we have the neighborhood area networks, which are Zigbee, NAN, and WSN. And beyond that, we already know that long range, up to 100 kilometers, we have cellular networks, 4G, 5G, and also low power wide area networks such as LoRa and Sigfox. So this is important to understand because the constraints are different for each type of these standards. Though many of them could be used for IoT, in this session, over the next 2 hours, I will concentrate mainly on the low power part of those networks. So some of the key standardization activities, if you look at these low power wireless sensor networks or IoT, IETF and Open Mobile Alliance, 1M2M, and Zigbee and WISN, they are leading most of the efforts, and most of these standards are already mature. In the last 4 to 5 years, a lot of standardization activities have happened. IPv6 and 6LoWPAN, routing algorithms such as Ripple, REST for IoT, COAP, and resource directory, etc. And in terms of security, DTLS and other cipher suits, they're all standardized by IETF. And Open Mobile Alliance came up with a lightweight M2M just above the COAP application protocol. And also they define the IPSO web objects for different parameters, whether we are doing humidity measurements or temperature measurements, they're all defined in terms of web objects. And 1M2M works a little bit more horizontally. They work towards the overall M2M standardization, basically the system standardization. They look at how you can do HTTP binding and how you can make COAP more secure and so on, and also bring in the device management aspects just above COAP. And Zigbee and Bison, they are predominantly the physical layer and the MAC layer technologies. That's what they concentrate on. Zigbee IP is an open standard. It's basically a 6-LoWPAN stack, mainly for the home area networks. And Zigbee NAN, Neighborhood Area Network, is for sub-gigahertz large area applications. And Bison is also a specialized standard, which works in both, it basically works in sub-gigahertz, and it's based on 15.4 standard. And there is also a lot of 6-LoWPAN activities and consortiums formed within Bison and Zigbee, which contribute to these standards. So if we look at a very generic communication scenario for IoT, we have on the left-hand side, you have a lot of wireless sensor devices. Those are all tiny devices, sensors. And the technologies that fall into this category are sub-gigahertz wireless sensor network, as well as 802.15.4 wireless sensor networks. So they work in usually different bandwidths. 868 megahertz is one of the popular bandwidths, and also 2.4 gigahertz, coinciding with a lot of other wireless technologies. So once those end devices are defined and you choose some of the technologies there, they need to be connected to a gateway kind of stuff. So you may have an access point or a border router in case of 6-LoWPAN. And then again, in order to connect to the internet part, you will need some kind of a server. So you have different servers based on the technology, and then also different protocols which will connect them to the internet part. So once you're in the internet part, you have a choice of Ethernet or LTE or Sigfox to connect to the external services. So then you have all the data from your sensor devices passing through your border routers, through the servers, through internet access standards, all the way to the cloud. And then you can use that data and push that data to either your mobile application or a web UI based on your use case. And again, if there is actuation involved, the reverse action happens. For example, from a mobile device, you get the reading of a temperature sensed by one of those sensors. But based on that value, you want to actuate something. So again, the same route back, right from mobile device back to your backend in the cloud, and then through the gateway, and then through another sensor or another end device connected in terms of wireless sensor networks. For example, based on a temperature, you may want to switch on your air conditioning or a fan or something like that. So that needs to come all the way backwards. This is important because in terms of stacks, because we'll be deep diving into different wireless sensor network protocols or IoT protocols, this is important to understand. So this will help us in gauging what all needs to be considered in order to build an end-to-end IoT application. So mainly the top layer is the application layer, and then you will need some data processing, and this is usually part of the platform. And then you have edge devices, and then at the end, the Internet of Things or the devices. So the device layer, the edge layer, the platform layer, and the application layer. So if someone is looking at building end-to-end, we need to have all these layers. So if we extend this stack, so we can divide it into data and network interoperability stacks. So on the bottom side, so you have the network interoperability. You have the hardware devices and sensors are sitting on those hardware devices. You have a transit network and you usually connect them to IP. So routing is involved. And then on top, you have the application protocol. But from a data interoperability perspective, you also need to take into consideration the APIs. It could be device to cloud interfaces, and then the data models, and then build applications on top of that. One of the examples of an application protocol on the left-hand side is MQTT. COAP and MQTT are very popularly used in IoT. And also some of the data models and APIs. Say one of the examples is SensorThings API, and there are many open source APIs that are available for a particular application that we can find. So going back to our core focus, that is low power IoT. So on the left hand side, you have the simplified OSI model. It's simplified because it's only showing 5 layers instead of the usual 7. So when we compare or when we translate this into the Wi-Fi stack, you have the Wi-Fi physical and data link layers at the bottom, and then you have the Internet Protocol as network layer, TCP as transport layer, and HTTP is usually the application layer with Wi-Fi. But when it comes to low power IoT stack based on 6LoWPAN, we have a lot of other protocol layers introduced. Of course, HTTP can be used, but it's not preferred. We'll come to know why. So COAP is there, MQTT is there. We can use it as an application layer. And when it comes to transport layer, of course, we can use TCP and UDP. Low power, the UDP is preferred. We'll understand why that is so. And also in terms of transport layer security, it would be either TLS and DTLS based on whether you use TCP or UDP. And of course, again, at the IP network layer, you have IPv6. On top of that, you have the Ripple routing protocol. And between the back and IP version 6, you have the 6LoWPAN layer. So this is an important introduction by IETF because the IPv6, the length of the IPv6 headers and the one that is required by 802.15.4 MAC are entirely different. So you need to convert that 1028 bytes into 127 bytes required for MAC of the 802.15.4. So you cannot directly convert 1028 to 127 without losing the information. So 6LoWPAN is introduced. We'll understand what it does and why is it required. And then again, you have the 15.4 MAC and PHY layers at the bottom. So the ones indicated in blue, they usually form the low power protocol stack for IoT. So we'll go back to another slide deck where we'll understand this from a different perspective. So usually from a device perspective, we are talking about the device because the constraints are always on the end device. The gateway or the um, technology that you use to connect to the internet or the cloud, they're not at all resource constrained. The resource constraint part is usually the end device. So end device is usually microcontroller based. That is how it is built for IoT. So typically a sensor node will have these components. One major is power source, the transceiver based on the technology used, and some external memory. and ADC connected to different sensors. Some of the devices are capable of connecting to or hosting multiple sensors, and some of them can host only a couple of sensors. So it depends on the device that is used. So if you see here, the resource constraints are in terms of the power, because most of these microcontroller based remotely used devices are running on battery. So power is a very big constraint. And also the memory, both RAM as well as the flash memory, ROM, are, are of very limited capacity in microcontroller based devices. So this is very important to understand, because whatever security or device management or whatever other feature, for example, the choice between UDP and TCP, choice between HTTP and MQTT or COAP, this is basically decided by the constraints that the device has, whether it is in terms of memory as well as power. So you can only write certain amount of code and flash it onto a device, because the moment you want to introduce security, for example, say TLS directly, you cannot really do that in microcontroller based devices. We'll talk about that why, but the constraints are very, very high. So the resources that are available to us in terms of memory, in order to burn the code that you write, even if it is very efficient, is very, very limited. So from that perspective, it's very important to understand that the code that we write into those devices has to be extremely efficient. And we also have to compromise on some of the aspects such that we cannot really have robust security, for example, and we cannot really have robust device management, for example, because of these constraints. We'll understand how and why. Um, Hardware platforms, yeah, there are many of them available. I think some of you, if you have worked on that, if you really work on wireless sensor networks, you will have come to play with these devices. Many of them, like CC2650, which supports both wireless sensor network as well as BLE. They're all very popular devices, and some of them, for example, NRF 51822, it also supports BLE. So you can use either BLE or 15.4 to communicate to the router part. So if you see an example, this is CC2650. So you can see that it has a temperature sensor. On the left-hand side, you can see that. It also has a motion sensor, and it has CC2650 MCU, microcontroller unit. It also has a digital humidity sensor. So it has RF connectors. It also has a pressure sensor and a light sensor and so on. So this is a TI CC2650, very popular end device that you can write your code into and use it as IoT device. So this is the other part. We'll leave that. And also there are a lot of IoT sensors that you can consider based on your application. So it could be accelerometer or air quality sensor or alcohol sensor, for example, barometric pressure sensor, and you can even include cameras. For example, if you're working on Raspberry Pis, you also have option to integrate camera into it. You can have a flow sensor integrated, and some of the very common sensors such as temperature and humidity and all that, you could really integrate into those devices. So we'll understand a little bit. I'm not going to talk a lot about Zigbee. I think many of us have heard about Zigbee. Zigbee is basically uh, higher layer protocols built on top of IEEE 802.15.4 standard. this is widely used as a wireless sensor network standard. So this was developed by Zigbee Alliance, and it's a public standard, but most of the implementations are proprietary. For example, there is a Z-Stack by TI that is very popular. And also, Zigbee is very general purpose. That is, it can cater to multiple application domains. And Zigbee defines three different roles, basically. One is the coordinator, second one is the router, and the third one is end device. So based on where you want to work, for example, if you're just working on the end device protocol development, the roles are a bit different. And the same device can be used as a coordinator, then the application code or the protocol layer code that you will write into that device is a bit different. So some of them are defined as RFT and FFT, which stand for reduced function device and full function device. So reduced function device can be used as an end device, and a full function device can be used both as an end device as well as a coordinator. So Zigbee allows for the same device donning the role of different devices. So Zigbee actually defines on top of 15.4 PHY and MAC a network layer, which basically includes routing, and also an application layer with a lot of profiles. There are profiles for home automation, healthcare, building automation, and so on. So you can use any of those profiles and build your application on top of that. And also Zigbee has some support for security. We'll not talk about that right away. As we said, it's built on top of 15.4, 5 and Mac. And then they have the network layer and the general operational framework. They define the multiplexing and security aspects here. And also different application objects in terms of different profiles, as we discussed earlier. And security is usually more horizontal across all these layers. I think we'll skip that. We have discussed that. We'll discuss this. So before we go to why we are discussing different protocols and why we need to consider the resource constraints of those devices, we can also try to understand a little bit about what is the difference between M2M and IoT. Machine-to-machine communication, it's not new. I mean, now even IoT is not new. It's pretty old now. M2M usually dealt with data silos, but IoT is more with regard to open data. So what it means is, so for a particular application, machine-to-machine communication had a direct interface between the application and the end devices. So the same thing couldn't be used for other applications. So it was all built as a very specific application-specific silo. But Internet of Things brings a lot of things together, and any application and any end device could be managed or connected through a common middleware. We call it as middleware. This could be cloud or non-cloud as well. So we define, or many of the people who built IoT, they came up with a term called middleware, where everything happens, where through which different applications can be connected, and also different devices based on the application. So M2M definitely is a subset of IoT, and it represents more of a vertical and closed point of view, whereas IoT goes beyond M2M, and it defines more of a horizontal approach, and it basically connects systems, people, and the things. So this is more of a IoT is a more of a broader perspective rather than M2M being a very closed point of view. So if you consider in terms of protocols, so as we said, we have a a constraint node on the right-hand side, so which talks IoT. We call this as an IoT device. And we have a gateway because that has to connect to the outside world. It cannot, most of them cannot connect on their own. Some of the Wi-Fi devices they can, but many of the wireless sensor network low power devices do not have any connection to the outside world, so they need a gateway to connect to the internet side. So the gateway becomes important because a lot of protocol translation happens at this layer, because on the IoT side, you have different protocols as we saw. For example, the application layer is COAP, and on the internet side, usually the application layer is HTTP. So the unconstrained world, which is the cloud and the unconstrained mode, for example, desktop version, that usually runs COAP. But also it's possible to run COAP on those devices, but it's usually not the case. It's usually run on HTTP. So in order to build the IoT, the protocol architecture looks like this. So you have the hardware abstraction layer where you have all these protocols, I2C or SPI, and all that. And also on top of that, you have an operating system layer. Usually, you cannot have, say, a Windows sitting on those devices. So IoT and wireless sensor networks, they usually use Contiki and very lightweight versions of Linux and FreeRTOS. And when it comes to Mac and Phi, as we said, 15.4, 6LoWPAN IPv6, and transport layer. So if we divide this into COAP and DTLS and UDP, so even DTLS as it is would not be possible in some of the constrained devices. There are different versions to constrained devices as defined by IETF. We'll go through that. So some of those will require tiny DTLS, so rundown version of DTLS. And if you're running a MQTT, so it usually runs on SSL and TCP. It's also possible to have it on some of the devices, IoT devices. And on top of that, you need to have some form of a message encoding. Usually JSON is used. EXI format can also be used. And on top of that, to have a device management, because you'll be connecting a lot of devices in an IoT network. So for example, if you're looking at a smart grid, there are millions of devices connected to the network. So how do you actually manage them? How do you patch them? How do you update them? So you need some kind of a device management layer which sits on top of the application layer. So this is defined by OMA, and it could also be a proprietary one. Many of the players have proprietary device management layers, but the leading industry standard is lightweight M2M. So let's begin with the device management layer. So why do we actually need device management in IoT? As I was discussing, if we want to perform remote management of all those end devices connected to the IoT network, we need some device management. So it performs both service enablement as well as application management. So it's not just about the end device, but also the service and the application as well. So some of the existing standards, I mean, the previously used standards, there is OMADM and TR069. They were not really built for constrained IoT devices. So we had to build a new lightweight version of the OMADM, which was formed. And so to replace existing standards in order to concentrate mainly on the IoT devices, lightweight M2M was born. It had to be simple and low cost because when you want to put lightweight M2M device management in those tiny devices, the size of the code or the object library that you will eventually burn into this device has to be very low. And also, it has to adhere to some of the architecture principles that make it lightweight. And also, it has to work on wireless connections because most of the IoT devices use wireless protocols. And the good thing is, lightweight M2M is architecturally based on REST. So it can run not only on COAP or MQTT, but also on HTTP. And the data model is extensible because it defines a few key things such as resources and the data model. And it is definitely designed with performance constraints of M2M devices. And the good thing is it adds security on top of uh, uh, COAP and DTLS. So once we use lightweight M2M, we don't have to lose track of the application layer and the transport layer security. It's all built into lightweight M2M. So in terms of deployment, this is important because we're not just trying to define a standard here, but we are actually trying to see how practical it is to take a standard or a protocol and implement it in terms of building an application or a system. So you have the endpoints and you have the lightweight M2M client and server layers. So basically, it defines the security, communication, and discovery layers. So once you are in the network, for example, the lightweight M2M client and the server, they have to talk to or go through these three different layers. So it defines end-to-end security, and it defines the web and data objects, which are part of the discovery part, and also management in terms of the communication as well as the storage and analytics, which come on the public cloud side or the private cloud side. So in terms of client server architecture, so what sits on the M2M device, that is the IoT device, is the lightweight M2M client. So it talks to the lightweight M2M server, which could be either on-prem or on the cloud, and various applications, your IoT applications or M2M applications can connect to that server. So on the right-hand side, I have shown how it usually looks on top of a IoT protocol stack. So the lightweight M2M stack sits on top of COAP. It is defined in terms of OMA resources. So in terms of the interfaces, it defines four different interfaces. One is for bootstrapping. The second one is for registration of those end devices. And the third one is the object or resource access. So once you have the objects defined as part of the client, you need to have access to them. So the object or resource access gives you access to those objects inside the client. And also you need some kind of reporting because whatever you're trying to manage or observe, that needs to be reported back to the server. So a reporting interface is also defined as part of lightweight M2M. And this stack is particularly efficient because the payload that is defined for lightweight M2M is very, very small. And it takes care of inbuilt support for COAP and DTLS, which is very good. And also it has UDP or SMS bearer, so you can define whichever transport layer you want to define. So you can use either UDP or SMS. So this is also important to understand. So resource basically is an integral part of lightweight M2M object model. So this is a piece of information made available by a lightweight M2M client. So for example, you have a temperature sensor, let's assume. So this temperature sensor will be giving out the values of temperature at well-defined intervals. For example, every 5 minutes, if you're sensing that temperature value, it will be provided by that sensor through the device it is sitting on. So this becomes a resource. Temperature becomes the resource. So each object, which is part of the client, can have multiple resources. As we saw in that TI device, it would be, or it could be hosting many sensors. So each sensor would be reading a resource, a value. So if you group or make them or bring them together, that becomes one object. So it's a logical group of resources in terms of lightweight M2M language. So as we said, it could be object 0, object 1, object 2, and many such objects inside a single client. So it can have any number of resources, and each of belong to an object. So this is important to understand from a protocol point of view. So once you have that lightweight M2M client setup, we need to talk to the server. So this is how the message flow works. So the client, the very first interface, as we saw, was the bootstrapping, right? So you need to bootstrap to the server. So the client usually sends a bootstrapping request to the server, and if it is approved, then the lightweight M2M bootstraps that client to the server. And once it is bootstrapped, this is optional. Some of them, they allow you to bootstrap by default, but this is usually the procedure. But bootstrapping is anyway optional. So once the bootstrap happens, the client has to register itself with the server. So it usually registers with the endpoint client name and the objects that it has defined. And then once it is approved, the registration is approved, the client lets the server know what all resources are hosted within the objects within the client. And once the server demands that I want to read this resource, the resource value hosted on the client has to be transferred to the server. And at the same time, the server can request a write resource. For example, it can create some of the new resources within an object inside the client. So, for example, it wants to write some of the values back into the client. It can also do so using the write resource command. And also, if it wants to observe some of the resources, say, for example, there are many resources or sensors available on the client, but it wants to observe only a couple of them, it can indicate that, and only those resource values will be returned by the client. And also, the client can be configured to notify, keep notifying certain resource values to the server so that without the observe feature, M2M, a lightweight M2M server is able to get some of the resource values. And if the client wants to deregister, for example, from your application, you want to take a client down from this communication and stop monitoring that device, you can deregister that client from the server, and then that device goes off the device management protocol. So this is how the lightweight management protocol works. So moving on to a layer below, which is the application protocols, you have multiple choices. So HTTP, which is based on the RESTful protocol, representational state transfer. COAP, COAP is also RESTful, but this is very, very optimized for IoT, that is constrained application protocol. And we also have the MQTT, message queuing telemetry transport, which is not a RESTful architecture, but this is mainly a pub sub model, publish subscribe model. And also we have XML based XMPP protocol, which is also used, but not very popularly used. So it's extensible messaging and presence protocol. So these are some of the application protocols that you will commonly find in wireless sensor networks or IoT. So how different they really are, because each application protocol is different. So CoAP is usually built on top of UDP as transport. So is MQTT as well as even XMPP can be used, but they usually are run over TCP. So what makes CoAP different is CoAP definitely cannot be used over TCP, making it very optimized. And because it is UDP, there is no guarantee of receipt of the, the packets that are sent over the network. So that is fine with IoT because even if I miss capturing temperature value, say at 12:30, and anyway I'm getting the value at 12:45, that doesn't make much of a difference. So UDP is fine with the IoT, most of the IoT applications, and the CoAP has very good binding with UDP. So the messaging is request response. So CoAP works on sending a request and getting a response. It's very common in RESTful architecture. XMPP and MQTT, they usually are built on publish, subscribe architecture. And HTTP, of course, as we know, this is TCP and request response model. And in terms of suitability with different communication protocols such as 2G, 3G, and 4G, where thousands of nodes are involved, all of them they support the extent of number of nodes that are involved. So it could be several thousands of devices. They all these protocols definitely support that. But in terms of LLM suitability, CoAP is really good, but all other protocols are okay with that. That is low power networking. Only CoAP is most suitable rather than the other three. So now coming to the constraints. So these are, so this is one of the main constraints, the compute resource. So CoAP and MQTT can work with very little RAM or flash. But HTTP, for example, it itself can work with similar flash or RAM, but when you have TCP as well as TLS protocol below that, you cannot really include all those protocol layers in the available compute resource. So moving on to CoAP a little bit in detail. So what happens is we have the internet and the constrained environment, as we already talked about it. So the proxy is required whenever you have a server on the internet side talking HTTP. If it is not HTTP, if the server is also talking CoAP, you won't need a proxy. So it can directly talk to a CoAP device on the constrained environment. So what CoAP does is, it's definitely sitting on top of the UDP and DTLS. It has a very compact 4-byte header. The header is so small, it's only 4 bytes. And it can support a lot of transport layer protocols, including UDP and SMS. Usually DTLS security is preferred. And it also has options or provisions for subscription and device discovery. So in terms of the methods, all the methods that you would see in a RESTful interaction, which is applicable for HTTP, for example, the get, post, put, and delete, all of them can be used for CoAP. And this is a binary protocol, meaning very low parsing complexity. Whenever you parse those headers and all that, the complexity is very, very low because of the size of the header itself. And the message size is also very small. Anyway, for example, if you're just transferring or using CoAP to transfer the temperature value or the humidity value, you don't really send a lot of information, right? So the message size could be as small as possible. So it usually prefers UDP. Basically, it works on top of UDP, but also it can run on top of SMS and USSD. MQTT is another one, message queuing and telemetry transport. It's standardized by OSS, so the version 3.1.1, that was the latest. And it uses the publish subscribe model. Um, and the publisher manages a list of resources, also known as topics. So subscriber can register for any of these topics to obtain information when an event occurs. So this is a very simple model, and there are a lot of open source MQTT um, implementations available if you want to integrate. RabbitMQ is one of them, if you have heard about it. So going down a bit, we covered the stuff, we covered the application layer. We can go a little bit deeper into COAP and DTLS, but right now I will just cover the general or generic principles. So security in IoT, of course, it includes all the main three principles, which are data encryption, source authentication, and message integrity. So what happens in data encryption is that you encrypt the message with a key, and then you decrypt that encrypted message with the same key, and you get back the message. So in terms of authentication, you need to know that the source which sent this message is an authenticated one. So you don't have to accept the message sent by an unauthenticated source. So you need to authenticate the source. And you also have to ensure that the message integrity is not compromised. What it means is the message sent by an authenticated source is the same as you received. So whatever you receive in the end shouldn't be attacked in the middle by anyone. So the message integrity is intact. So there are different mechanisms how you encrypt data, how you authenticate a source, and how you maintain the integrity of messages. We'll go a bit deeper into them a little bit later. So I think we already covered this. The If you're trying to build a co-op-based application and you're considering a scenario where you're dealing with a HTTP server, then you also have to consider a border router capable of all these protocol translations. It will involve the HTTP to COAP, TLS to DTLS, and TCP to UDP. So this may look simple on this diagram, but when you implement this, the border router becomes quite challenging because putting COAP, DTLS, and UDP on a client could be easier, of course, based on the constraints. And the server is anyway not a problem. You already have HTTP, TLS, and TCP support. But the border router, you need to have um, a very efficient way of protocol translations from HTTP to COAP, TLS to DTLS, and TCP to UDP without compromising on the quality and the quantity of the information that is being transferred. So then what happens is the TLS-DTLS bridge that becomes pretty important. So how it is usually built is like this. So you need to have an abstraction layer because the APIs for TLS and DTLS, they are a bit different. You cannot, there is no direct binding between those APIs. So you need an abstraction layer on top. So usually the TLS module consists of 4 sublayers: the application, alert, change cipher spec, and the handshake. And the record layer usually has facilities for fragmentation, integrity checks, authentication, and encryption. So DTLS is definitely built on the same principles as TLS. But inside DTLS, you need to, for example, if you start implementing DTLS based on the IETF standard, so what you need to consider are these different blocks. For example, you need to have a functionality to handle the clock. You will also need a random number generator, and you need to choose between the crypto algorithms available. Usually AES is used for symmetric cryptography. Along with that, you also need CCM for authentication. And hashing is usually done by SHA-2. And also how you allocate memory. For example, in terms of memory allocation for DTLS, this is handled a bit differently than TLS. And there is also a queue. For example, because it operates on top of UDP, you can define a net queue for messaging, and you have to handle that net queue, a message queue, based on the application layer, how it is actually defined. So based on that, you can keep some of the information in the queue and process it in real time whenever the device wakes up or something like that, based on the application COAP layer, how it is built and how it is configured for your application. So if you cannot actually implement DTLS as it is, as defined in the standard, there is also something called as lightweight DTLS. So there are different options how you can implement this. You can implement it with a simple pre-shared key, which is called PSK. And you can also have a raw public key, which is called RPK. And also you can use some certificates, lightweight certificates. And there is a very nice implementation called TinyDTLS, which implements PSK only, that is pre-shared keys. It also supports hashing in terms of SHA-256, and it uses AES CCM for encryption. So there is also a lightweight version of TinyDTLS, which we tried. We have some papers on that. You can get access to them on ResearchGate. How you can implement TinyDTLS, lightweight version of TinyDTLS, where we remove CCM, so there is no authentication. And this is not fully compliant to DTLS, but still, it works and it provides the required security layer at the transport layer, and class 0 compliant. So I will come to the different class of devices defined by IETF. So class 0 is the most resource constrained. So if you want to have some kind of security, even in class 0 compliant devices, we can go with lightweight version of TinyDTLS. And this was built on top of TinyOS. So where we have secure COP, that is not only the lightweight TinyDTLS, but DTLS version plus COAP plus 6LoWPAN, and this is compliant to class 1. So in terms of devices, IETF defines low power devices for IoT in terms of class 0, class 1, and class 2. See, class 0 is, if you see the RAM size, it's much less than 10 kilobytes. So this is very, very low. And the flash memory available is much, much less than 100 kilobytes. So I remember some of the analog devices um, uh, chipsets that we used, which came with just 86 kilobytes of flash. So that is definitely class 0. And it had about 10 or 8 kilobytes of RAM. So that is class 0. And if you want to put all these protocol layers, that is COAP, DTLS, 6LoWPAN, it's pretty tough on them. So you cannot really go for that kind of implementation. So you need to have lightweight version of TinyDTLS sitting there. Class 1 is much better. You will have at least around 12 to 16 kilobytes of RAM and about 100 kilobytes of flash. Class 2 is you can have the full version of DTLS plus COAP and even lightweight M2M. And it also comes with 250 kilobytes of flash, or even now some of them 512 kilobytes of flash. You cannot compare them to any of the devices you may have played around with, such as Raspberry Pi and all that. They go beyond these RAM and ROM figures, but these are the IETF device classes for very low power IoT devices. For example, if you want to put a device in a mine running on capable of running on a battery for 3 years, then class 0, class 1, class 2, they need to be considered because they consume very little power and they can run for years. So if we want to put very efficient protocol stack, including security, then we need to consider these classes. Skip that. So going a bit below security, that is DTLS. So there is the 6-LoWPAN layer. So as I said, the MTU for IPv6 is 1280 bytes. So this is a layer sitting between the IP and the MAC, 15.4 MAC. So this is called as an abstraction layer so that you can abstract the IPv6 into the 15.4 MAC. So 6LoWPAN allows that, and it brings IP to all the resource constrained IoT devices. So that's the beauty of 6LoWPAN. That is how the IoT was born, making use of these microcontroller based devices so that even they could be connected to the internet side. So from a MTU of 1280 bytes in IPv6, we need to have it adapted to 127 bytes of MAC layer on 15.4. So that is achieved by 6LoWPAN. What it actually does is it compresses the header, and it also allows you to generate a IID, the unique identifier, because this is used for addressing. And also it has support for mesh routing protocol, because even if you talk about Zigbee, it supports mesh. And 6LoWPAN also does support mesh. And so it also has compatibility between the broadcast header between IPv6 multicast to 15.4 broadcast, because 15.4 doesn't do multicast, but it can do broadcast. But IPv6 is built on multicasting technology. So 6LoWPAN kind of bridges this gap between the multicast IPv6 and broadcast 15.4. So what are the problems that 6LoWPAN actually solves? So one of the main problems that it solves, as I already indicated, is the MTU, maximum transmission rate, from 1280 bytes of IPv6 to a maximum MAC frame size of 127 bytes. So 127 bytes is usually consisting of 102 bytes for payload. It includes the 81 bytes for security and 40 bytes for IPv6 header. So only 41 bytes for the upper layers and 4 to 8 bytes for the UDP header. So the application layer is left with only 33 bytes. So what happens is it fragments the packet, and also it can do the reassembly in the reverse direction. So both packet fragmentation as well as packet reassembly is carried out by the 6LoWPAN adaptation layer. And it also does the header compression of IPv6 and the TLS layer on top of that. So we'll not go into the details of how it's actually done, because this is more of a implementation issue when you really start implementing 6LoWPAN. As of now, we have lot of implementations already available as open source. So you don't really have to write code for 6LoWPAN, but you can directly integrate it. Well-defined APIs are there, and you can start running your application through proper integrations into your stack. So there is some improvement over 6LoWPAN. So if you are considering time-slotted channel hopping, for example, TSCH, there is 6-dish, that is IPv6 over TSCH mode of 15.4e. So the basic 15.4 was an old standard, and that has been replaced by E and YAF in 2016. So 6 TCH that defines the IPv6 over time-slotted channel hopping. So this is mainly standard for industrial automation and process control because many of the applications demand that. And this standard is inherited from Wireless HART and ISA 100.11a, which are more for the industrial automation. So this is definitely not low power. This is more, usually the devices are always powered. And there is also 6LoW, which is IPv6 over networks of resource constrained nodes. There are several RFCs and other stuff that have been part of IETF. I think this has been updated now. We have a lot of stuff in terms of RFC 7428 and 7400. Basically dealing with header compression, further header compression, and transmitting IPv6 over other networks. So we'll not go there. There is also a standard on how you can transfer data over IPv6 on top of BLE. This has also now been standardized. So you can also look into this if you're trying to use BLE in some of your implementations. And there is also alternative called Thread. Thread also sits on top of 15.4 MAC and PHY, and it also uses 6LoWPAN, but very much more efficient version of 6LoWPAN. And they've also made the IP routing. They don't use Ripple, but they use their own routing protocol that is also more optimized. And again, it uses UDP, and application layer is up to you. You can use COAP or MQTT as you wish. So they basically define the optimized versions of the transport layer, the routing layer, and the 6LoWPAN layer. And they have included a lot of security features and also commissioning features for the end devices. So that makes Thread a very good standard. It's not just a protocol, but they have defined multiple protocols within their standard. So let me go back to the earlier slide, and this is where we had stopped. So we just covered the lightweight M2M stuff. It's already covered. Not go here. Yeah, so COAP, I think we can also go into a bit of details of COAP. Security, yeah, I can talk a little bit more about security. So if you look at any of the core IoT challenges, security is usually listed as one of the topmost. Why? Because there are many attack surfaces when it comes to IoT devices. So for example, if you consider this scenario where a lot of things are connected to the internet, it can be your light bulb, it can be your music system, it can be your refrigerator, or it can be even your smart car, or it could be a heart monitoring device. So there are different security holes and attack surfaces, and the intentions are also different. Somebody could be just trying to take control, and somebody could be trying to steal information, and some other hackers or attackers could be even trying to disrupt services. So in all these scenarios, security becomes very important. For example, if somebody is just trying to take control of your light bulb, it doesn't really matter much. Um, so is your music system. Somebody is trying to steal information out of your music system. It may not be very critical, but taking control of your car, for example, smart car, by hacking into it is pretty severe. And if somebody has the ability to hack into your heart monitoring system and try to disrupt services, then it can be life-threatening. So attack surfaces are different. The intentions of the attackers are also different, and it also depends on the application under consideration. So it makes security very important for IoT. If you look at some of the major security breaches in the last few years, some of the major ones were BrickerBot in April 2017. It actually was a permanent denial of service attack. Um, the permanent denial of service basically it kills the end devices, and it was launched by compromising many of the IoT devices in the network and by corrupting their storage. So this is very significant because the the its predecessor, like Mirai bot, which was in October 2016, which was a denial of service attack. It used the internet's DNS infrastructure, basically the DYN servers. It was launched using many of the IoT, unsuspecting IoT devices. So those devices were used to launch a distributed attack. So several service providers like Amazon, Twitter, CNN were down for several days. You can imagine the situation when Amazon can be down for, say, several hours. So it was a case of several days. And this is why the secure device management becomes important. The problem is there is always a broken chain of trust. So, for example, there is the device layer and the connectivity layer, and then we are running IoT applications and doing some analytics on top of that. But all those data sources are pretty much unmanaged, and in many cases, wherever the data is being transmitted, the network is not really trusted. So this doesn't add much value. So you can intercept and manipulate data in transit if the network is untrusted. So this is usually called the man in the middle attack. And you can actually compromise those end devices if they are unmanaged. So you can have direct access to the data, and you can also do side loading on them. And many of them, because they are connected to the internet or some network, you can access them remotely as well. So the main problem is the broken chain of trust. So how do you actually solve them? So you need to manage those end points, basically the IoT devices. So what you need to do is, as we saw in the case of lightweight M2M, you add a device management layer. So what it does is it makes the connections secure, and also data connectivity becomes secure, and all the data that is coming to your applications and the analytics engines that you're running, they add more value because nobody is able to steal data directly connecting to those devices. And also virtually or remotely, you cannot connect to those devices because device management usually involves two-way authentication between the source and destination. And usually the delivery of data is from a trusted source only after the authentication is done. And it involves using a lot of encryption, keys, and certificates. So secure device management is one of the best solution for end-to-end security. As we discussed in case of DTLS, why it has to be DTLS and why it cannot be TLS, or even some lightweight versions of DTLS or tiny DTLS. This is mainly because of the resource constrained nature of those devices in terms of available memory, computational capability, and the power management issues. But there are definitely challenges. You need to choose the suitable authentication and authorization mechanisms and the key management. For example, how do you actually manage those keys in those protocols? It's very important. And also the crypto algorithms that you choose, they have to be lightweight and and it also depends on at which layer you want to use those security mechanisms. For example, some of them they may settle for just MAC layer encryption, and some may go all the way up to transport layer security, and some of them may choose end-to-end security. For example, all the way up to COAP, that is making it secure COAP, and also lightweight M2M layer, that is the device management layer. So it basically depends on what kind of application it is, whether you're transferring sensitive data or very little sensitive data or totally non-sensitive data. So depending upon that, you can encrypt or try to encrypt different layers of the protocol stack. We've already spoken about this. So in terms of the tech directions, how it is moving. So the IoT stack that we spoke about earlier, so that is becoming more integrated. So earlier there was no middleware as we talked about. So a lot of people have come up with a platform to manage all your devices, your data management, your APIs, and the applications, and on top of that your mobile applications or the web UIs and all that. So everything is part of the PaaS. So that becomes the middleware. So you only connect the middleware to your end devices to manage most of those IoT devices. And earlier, as we saw a generic stack, now it is becoming more converged. So what happens is the application layer need not go through the data processing and the edge, but it can directly talk to the thing or the IoT device. So one of the good examples is the embedded Android. I think some of you might have worked on it. So it allows you to talk directly from the application layer to your device, so IoT device. So that makes it more efficient in terms of implementation for constrained devices. So if you look at top 10 technologies for IoT, security and device management are always in the top five, even still today. So there are many others, for example, the standards and ecosystems, because there is not just one. In terms of standardization, the lightweight M2M technical specification, when we implemented like in 2014-15, it was version 1.1. Now the latest is the 1.2, and they also have test specification. For example, if you want to test your client device against a open source lightweight M2M server, you can use the test specification, which is version 1.0. And if you want to make use of the ready-made standard objects, which is defined by our IPSO Alliance, you can also make use of them, and you can integrate that with the OMA lightweight M2M. So it becomes very easier to run your application. So in terms of IoT security, there are a lot of standards that have come up. The IETF RFC 7925, like 4 years back, they have the DIE standard, DTLS in constrained environments. If you want to implement and make it more efficient and make it available for open source, you can do that. You can still do that. So you have to follow this standard, RFC 7925. These are all open standards. You can download it and start implementing if you wish to. So what it does is a very minimal profile of DTLS for use in IoT. So this is defined, standardized. So it will be compatible with anybody who implements RFC 7925. So compatibility is ensured. And there is also a standard for authentication and authorization in constrained environments. So this is standardized by RFC 7744. It also defines a lot of use cases and the requirements therein. It basically focuses on COAP and DTLS for providing access to resources. So that is, it's a good combination to use RFC 7744 and RFC 7925 in combination, because then you will be compliant, fully compliant from a security perspective, both in terms of the cryptos, the encryptions, the authentication, as well as authorization. So it's the end-to-end security mechanism if you want to implement it. So in terms of where actually the security technical directions are going, still the gateway is an important, because there is still a lot of improvement possible in the gateway. Um, if you want to introduce session-based security at the gateway, which will be more flexible and provides the end-to-end security, this option. And whenever we are implementing security in IoT, we have to remember that it is basically a chain, and at different points in the protocol stack, you can introduce security. For example, you can just, as I mentioned, you can just introduce link layer security at the MAC layer. You can go all the way up to transport layer or application layer, and cloud security and so on. So basically, it depends on the application. So it's also important to consider implementation combinations rather than just going for software implementations or hardware implementations, because in terms of memory footprint, you cannot just implement everything in software. So some of the chipsets, for example, the TI and analog devices chipsets, they already have a crypto module, say AES hardware module already built in. So you don't really have to build AES encryption in software. So you can make use of the hardware module and build on top of that. So that becomes very good for efficiency in terms of both memory as well as energy. So it's always good to consider a combination of hardware and software cryptos whenever you're implementing security. And it's also important to be compliant with some standards, because otherwise your devices will not be compatible with other devices. For example, if you're concentrating on building a IoT end device and you want to connect to any border router, for example, it has to be compliant. So if both of them are compliant to IETF standards, then there is no problem. Otherwise, it becomes very proprietary, and there will not be many takers for that. And if you want to check the interoperability of your implementation, you can always consider the plug test provided by ETSI. It's a European Telecom Standards Institute. So they do these plug tests from time to time. If you have a new implementation which you think is more optimized, you can always go for plug tests and play around with other players and test for interoperability. There is also a lot of recent talk about blockchain for IoT security. It can be used in some of the scenarios, if not in every scenario that IoT considers. So you can also look at the blockchain option for IoT. Some of the industrial scenarios, Industry 4.0 scenarios, if there are too many transactions, and if you want to use a distributed ledger kind of stuff to keep a track on all the events that are happening. So you can use blockchain for that. And that also adds on top of IoT security. So I still have a deep dive on COAP and DTLS. I think we can use the next 15 to 20 minutes to cover that, if because going a bit deeper into COAP and DTLS always helps. And after that, I will start taking the questions. think we have already addressed this. Okay, so let's go directly into the COAP deep dive. So CO in COAP stands for constraint. So basically, it's a binary protocol and very compact. As we said, a 4-byte header. This is the header. This is how it looks like. So there is a message ID and there is a version part. And if we want to use tokens, if that is also possible, and the payload version also. So payload is not a lot because this is not actually required in IoT applications, as I already explained. So what makes it very efficient CoAP is that because of the 4-byte very small header, it's very simple to decode. And this targets 8-bit microprocessors. So you can even have this on those low power devices running on microprocessors and microcontrollers. So, for example, the application part, the A in CoAP stands for the application. So this is built on REST, as we already discussed. So you can still continue using all the get, put, post, and delete messages as part of the REST paradigm. So a typical URI resource indicator looks like this. For example, we know that HTTP colon slash slash, that is how we use. Instead of that, we will use CoAP colon slash slash. And what happens is you have a sensor in your home. So for example, in room one, you have a sensor. Room two, you may have another sensor. Room one sensor is measuring temperature. Say room two is measuring humidity, for example. And this is how it looks. It's very easy to understand. I don't the syntax is so simple. Everybody, even reading it for the first time, will understand that this particular URI is trying to return the maximum temperature value of the sensor in room one. So that is pretty simple. So another example could be the minimum temperature value in room two using another sensor, or the current humidity value from your living room using another sensor. So it's pretty simple to use the CoAP protocol. So the URI defined is very simple. So of course it is the protocol part is built on UDP to save the bandwidth for IoT. And also the protocol part includes DTLS, as we already discussed. So in terms of the usage, again, HTTP methods, all the get, put, post, delete methods. And it also supports some status codes as you see in HTTP. And of course, it is based on URIs. And so low memory, low bandwidth, high rate of packet failure, and low power. Of course, the packet failure rate will be high because it runs on UDP. But that is how it is efficient for constrained environments and IoT. And it has the option to carry different types of payloads, and also it can identify them. And you can use different data serialization formats such as XML, JSON, CBOR, etc. So it is from that point of view, it is pretty flexible. It supports a lot of payloads and gives you option to serialize your data. I think we've already discussed that. We'll not go here again. So in terms of how it is different from HTTP, it runs over UDP, not TCP. And in HTTP, you usually use text headers, but in CoAP, you will definitely use binary headers, which are very compact. So header, if you compare it with HTTP, the number of options available to you is much, much reduced. And also the reduced set of methods. For example, there is one more method called as observe. That is an addition in CoAP. So you can just keep observing a resource instead of querying every time, so that that device can go to sleep whenever required. And there are different message types supported. For example, the CON, non, ACK, and RST. So they stand for confirmed, non-confirmed, acknowledgement, and reset. So the response codes are also reduced, and also the content formats are also reduced. So the request response empty, they all deal with the uh, confirmation, non-confirmation, acknowledgement, and reset based on your application. So discovery and metadata in terms of COAP usage. You can issue a get on this URI, for example, the .well-known core to get status on any of the resources that you use. So it will connect to all the known resources and discover them and get you back all the metadata that is associated with that resource. One good thing about COAP is you can issue a get method, the observer option, so that saves you a lot of bandwidth and also the handshakes required between the client and the server. So this actually adds to the efficiency of the COAP protocol as well. So whenever there is a change in value, the resource pushes that data back to the client, and then client comes back to life from its sleep mode, and then the value is pushed back to the server. So observe option for the server makes COAP very efficient as well. So one of the examples, I think I already talked about this. Um, so the request response in COAP, this is how it works. So for example, the on the bottom part of the slide, you have the URI, COAP, my home, 5683 is the port. So this is the in secure mode, that is non-secure mode. You will use the UDP port 5683. If you're using DTLS in combination with COAP, you would use 5684, which is the secure UDP port. So for example, this temperature sensor is in your bedroom. So that is the name of the parameter the device controls. So that is temperature here. And the name of the sensor device is the Nest underscore bedroom. And port 5683 is the default COAP port. And the name of the protocol is the COAP. So this is how the URI is defined. So what happens is, so for example, you're querying from your end device. So your device is your mobile phone, and the end device is the temperature sensor thermostat in your bedroom. And for example, if there are two thermostats, one in your bedroom and another one in your living room, so they become the servers. So in COAP language, the server and the client are interchanged. So the end device, which is sending the values, becomes the server. So this is the reverse in HTTP. So that is one important thing to remember. So whenever you make a query to that COAP server, so your URI will be COAP my home 5683 port Nest bedroom temperature. So the return value will be 72 Fahrenheit, whatever. If it is in centigrade, it will return a centigrade value. So the similar URI, if you want to query your server in the living room, so nest underscore living room and again temperature, it will return another value. So this is how the COAP works. Pretty simple, pretty straightforward, and it's also very easy to configure if you're using it on the end devices. Similar to HTTP, it has the status codes. So, for example, you have the 400 or 500 status codes in HTTP, right? So similarly, 4.05, 4.06, and 5.00, they are used in COAP. So pretty similar, whether it is for client error or redirection or successful or even internal server errors. Most of those status codes are implemented in COAP as well. So whenever you want to catch packets using a packet analyzer and want to see how the protocol implementation is going, you can make use of the status codes and make sure that everything is fine. So this is the main stuff, that is the message format. This is the header. The header consists of the 4 bytes, as I said. The version, that is COAP version number, RFC, based on the RFC version. And the T stands for the type of COAP message. It can be confirmed, non-confirmed, acknowledged, or reset. And there is also an option to indicate the token length. And you also have the code for the request response. So it's usually c.dd. So 0.00 will be an empty message. And also a message ID. So each message is assigned an ID. And this will help in detecting the message duplication so that you don't have to keep sending the same message repeatedly. And there is also a token of 0 to 8 bytes. And also the type length value format, COAP gives you several options. And the payload is also, again, up to you. It's usually less than 3 bytes. So this message format in COAP is very simple and very straightforward. And open source, you can actually implement some of the stuff for COAP. There are many servers available open source, so you can test your client against the servers. Some of them are hosted in ETH, Zurich. There is also a coap.me, runs on 5683. These are all non-secure. They don't have the DTLS version, so you cannot test your DTLS version in this. There is also a C library available, for example, RBM stack for Contiki, so it can run on Contiki. And if you want to use TinyOS or Riot operating systems, so there is also libcoap, so you can use those libraries and try to build it on your client or the server. And also, if you want to use Java, there is Eclipse Californium. You can use that implementation. And there's also Apache version. You can use that. And if you want to run or test it on a browser, for example, there is a plugin called as Copper. Firefox has this client plugin. You can also use that. And if you want to learn more about COAP, there is a very good website called coap.technology. You can always refer to that, and all the latest stuff is available there. So moving on to some practical aspects of DTLS, this will take another 5 to 10 minutes, and after that we'll open the floor for questions. So when we started implementing security for IoT, right? So we were basically working on the client side of those devices. So we started from the low hanging fruit. So we wanted to take the MAC layer security into advantage and provide just the MAC layer security. So, for example, the end node, there are different end nodes, and they are talking to the border router over 802.15.4 standard. So there is no application layer involved here. This is just the MAC layer part. So you have the MAC security. You have to implement both on the end node as well as the border router that you're working on. So there is PHY and MAC, there is PHY and MAC, and then on top of the data link layer, you need to introduce the MAC layer security. So if you want to consider end-to-end security, you have to go beyond that MAC layer security and also bring in the internet side of things, as I said. So it involves the sensor devices on the left-hand side, your constraint network, your IoT gateway, plus the internet. So you not only need to introduce security, but also take care of the protocol translations in terms of COAP, HTTP, DTLS-TLS, and UDP, TCP. If you want to compare DTLS against IPsec, basically DTLS is an application or transport layer security, whereas IPsec is only at the network layer. And IPsec is usually implemented in OS kernel, and it has limited support, basically, if you want to take it to embedded devices. And if you want to put it on IoT devices, there is significant overheads to consider, so that is ruled out. So DTLS is more flexible in terms of its implementation because it's an application space, and you can use some of the TLS infrastructure, reuse it, so that gives you more flexibility. And overheads are very minimal, and it has inbuilt binding with COAP, so it gives you end-to-end security whenever you're considering COAP. I think we have already explained this. We can skip this. I think we've already spoken about this. So this is again discussed earlier, just a little bit of more details here. So clock handling and random number generation, you can use it for computation of your secret keys. AES in control mode, you can use this for encryption. CBC MAC, which forms the CCM format, also used in Wi-Fi. This is used for authentication and hashing of the messages. You can use SHA-2. Also, as I discussed, memory allocation. Because of these constrained devices, you have to allocate and free memory of time. So memory allocation, even for DTLS, becomes very important. And also to manage all the messages to and from the network, you need to maintain a queue. So these are all the main or core parts of implementation that you have to consider whenever you're trying to implement DTLS. So how does it interact, the DTLS part, if you start implementing? So on top, you will have to interact with COAP. So you will have the AEAD cipher suite, authenticated encryption with associated data. So CCM and GCM are both examples of AEAD cipher suite. And also, you can use the 8-octet authentication tag with CCM, which is more computationally efficient, and it will also conserve a lot of bandwidth for you. So these are the options you can consider for DTLS, and you have to keep in mind that you have to interact with COAP on top as well as UDP below that. So in terms of forward and reverse message interaction, you have a normal packet coming from COAP and then the encrypted packet from DTLS to COAP in the forward direction. And in the reverse direction from the server to client, you have the secure UDP packet coming to DTLS, and then you decrypt it and send it back to COAP for further processing. So DTLS, it involves a handshake between the client and server, and a lot of key exchanges happen. So there are usually 6 flights. This is still very heavy for constrained devices. You can think of making this more efficient if you can, but this is the standard defined in DTLS. So in flight 1, the client says hello to the server, and server verifies that request. And then after that request, the client says client hello again with some token sent along with that message. So that token is used for the subsequent messages, and the server sends you the server certificate, and then server is done with the hello, and then the client key exchange starts, and it will also indicate which cipher suite it will use in this message, and then the client is done with its message, and then the server indicates that this is the cipher spec we'll use for all the interactions. If there is a change in cipher, the client has to indicate that, and the server okays that. And then once the change cipher spec is agreed between the client and server, all the communication between client and server happens in an encrypted form. All the application data is always encrypted between the client and server. So whenever client wants to change the cipher, so it has to start requesting to the server in terms of the flight 3 and 4. So only then flight 6, whenever it is agreed by the server, the new cipher spec can be uh, included and encrypted in the subsequent communication. So in terms of APIs, there are different interfaces you need to consider. So one is reading from the peer and sending it to the peer. So you need to consider the context and the session and the data and its size. So these are the API constructs that you can consider. So you need to write a binding element both on the COAP side as well as UDP side. So whenever you're reading from a peer, whether it is UDP in the reverse direction or from COAP in the forward direction, you have to use these APIs. So when we implemented, we considered different options. One was the software implementation. So everything in software, TinyDTLS, that was operating system. The authentication part, CCM, is in software. So AES 128, again in software. The CBC Mac, again in software. And even hashing in software. So this was a complete software implementation. And complete hardware implementation is also possible. So some of the chipsets, they come with CCM in hardware as well as hashing in hardware. But hybrid implementation, that gives you a better option. So usually the AES 128, that is allowed or available in some of the hardware modules, some of the chipsets. So you can make use of that and then only implement CCM in software, so the authentication part, and also use hash in software over TinyDTLS. Whenever we did comparisons, this gave us the best results. So you can refer to my papers in ResearchGate. We have very um, um, exhaustive uh, uh, implementation comparisons done, both software, hardware, and combos. So you can go through that and consider whatever is suitable for you. So in terms of performance, we considered memory footprint, packet overload, and the energy part. So these were the deciding factors for performance. So whenever we implemented COAP, the overhead was 17 bytes per frame. And whenever we introduced DTLS, it added 29 more bytes. So this is pretty high. And we saw that DTLS, it will consume considerable energy and introduce a lot of delays as well. So whenever DTLS is introduced, the energy consumption part, for example, if you're running on battery, for example, if it runs for 3 years and you introduce DTLS security, your device will only last for 1 year or less than 1 year. So energy consumption part by introducing DTLS increases by 3.2x, even if it is very efficient implementation of DTLS. And also DTLS will introduce 8 milliseconds of delay in every co-op transaction. So 8 milliseconds of delay you need to account for whenever you're implementing that. I think we have talked about this. Also this. Will not go into these details because this is more about the protocols. Back to the previous slide. So you can always contact me on this email ID if you have any questions. And as part of the Computer Society, we are also available through the Bangalore Section website. Our website is cs.ieeebangalore.org. You can follow us on LinkedIn and Facebook as well. And if you have any direct questions on IoT protocols or DTLS or lightweight M2M, please feel free to contact me on this email ID. And let's go back to the questions. So let me see the chat window. Okay. I don't see any questions, Prashant. So if you have access to some of the questions, can you please read them for me so that I can answer?
So Vishwas, I don't think participants have posted any questions So just
Okay.
an open call to all participants. I think we have another 5 to 7 minutes more. So please feel free to post your questions in the chat window.
Yeah, we have still 8 minutes left, so not an issue. So keep posting your questions, and I'll be happy to answer them. And before that, I'd like to thank the IEEE Bangalore section for this opportunity. It's always great to interact with students, and hopefully this will add to their skill development and lead to further innovation in IoT or security or device management. I'll be happy to help in whichever way possible.
Thanks, Vishwas. I think even I think we are very fortunate to actually get you speak on this topic because we understand the type of engagements you are in and you are always occupied. So we thank you from the IEEE section point of view to spare this time and speak to students. I think the session was quite in depth. I think you covered the breadth for the first 40 minutes or so, and then you went to depth of specific protocols. And I can see that this model will work very well for both for students who typically want to know what is IoT and what are the basic elements they should be aware of, while it will also benefit students who really want to understand the nitty-gritty details of certain protocols in the IoT domain. So I think it was a win-win for both ends. So thank you for preparing this presentation and delivering this talk. So Vishwas, I don't think participants will post any more questions. We have given them time. So
Okay.
if you have any last concluding comments, you can probably mention that, and we'll probably sign off from there.
Yeah, sure, Prashant. So, yeah, definitely. Main intention of this session was to bring out the practical aspects of IoT protocol stack implementation. We know that this phase might have passed in building very efficient low power IoT end devices, but there are still challenges in terms of security, as I said, and also device management as we hop on to larger application domains. So it's very important to consider device management as part of the design rather than thinking of it as an afterthought. So both the device management and security, I think I would suggest to include them as part of the design. Whoever wants to implement protocol stacks in their devices or even the border router cases. So that will make it robust, not only from a security point of view, but from the implementation of end-to-end protocol stacks for the IoT ecosystem. Because the moment you introduce device management, that will bring in very efficient application protocols as well as security considerations and so forth. So you don't have to go back to measuring which device type I need to consider and all that. So you have that in mind from the very beginning, from the design phase, so that it's more efficient. And also from the experience of implementing these protocols hands-on, I can say that there is a lot of scope for implementation and making the code more efficient. So whoever can implement device management plus security in a class zero device even today, I think they'll be stars going forward because if you can do so, even you can run them on battery operated, very resource constrained IoT devices. It's not very easy to do, but yeah, if you can come up with efficient, optimized code for security and device management using the existing protocols and the recommendations available in terms of standards, that would be really great. So even if some of the um, open source implementations are already there, you can directly use them, but there is also a lot of scope for further improvement and making those protocols much more efficient. So
So Vishwas, we have one question that has come now.
Yeah.
So the question reads as follows. It is from A and Navanish. So the question
Okay.
is, how much delay due to security features can be tolerated?
Yeah.
So I'm
So
not sure if the delay here means the end-to-end delay, the application level delay. Is that what the speaker means? So essentially, the question is that if you end up implementing the security features, how much delay are we going to encounter, or how much overhead? Let's put it in a better. How much overhead are we going to encounter?
yeah, it's a very good question actually. See, this has to be answered in two phases. The phase one is the protocol implementation aspect. Okay. So whenever you introduce DTLS, that is for security, as part of your COAP-based IoT implementation stack. So that will definitely include some delays. As we said, with my or with our implementation previously, it was a delay of 8 milliseconds per COP packet. So that is quite a significant delay. But on the other hand, if you look at the delay from the implementation or the application point of view, it may not be very significant because most of those IoT devices will be in sleep mode most of the times, and they will be sending this information, say, every 5 minutes or every 10 minutes. So most of those devices have a buffer option, and you will be sending those messages whenever the device wakes up. And if you want to, even if you want to implement security and transfer this information in a secure manner, this is tolerable. I don't see a problem from a application point of view, but definitely if you introduce DTLS, it will introduce some delays in packets reaching the server from the client.
Okay. So I think there are some other general questions. I think they are pointed to us. I think the first question is from Nandini Patil. So the question says, can we get the recording? Of course, the session is being recorded. The protocol that we follow is we share the recording with the speaker, and once the speaker approves the recording, we then post it in our YouTube channel, and the YouTube
Sure.
channel goes by the name IEEE Bangalore. So this will take a week from now because there are four lectures in the series. So we will be contacting all the four speakers and getting the approvals, and we'll proceed. So, but of course, once the recordings are there, we will notify you. So yes, you will get the recordings. And the second question is from Professor Lina Sultana. She is asking, can you please share the content? So I think, Madam, I think the recording will be there. So the recording will have all of these things. So that will serve the purpose of both the slides or the presentations that you want to take a look at, as well as the entire lecture that the speaker has just delivered. So it will work both ways. Okay. But give us at least a week before we notify you regarding the making the recordings public. So I think we are at 2 p.m. So if there are no more questions, we'd like to thank Dr. Vishwas Lakkundi once again, and we hope that we will be able to invite you to further such seminar series in the future, which will focus on IoT and IoT protocols and security specific. So with that, Vishwas, thank you. We will sign off.
Thank you, Prashant. It was my pleasure.
Thank you.